So yeah, let's treat this as a little experiment, you and me. Here's how we're going to do it. We'll start with the official, formal definition, the textbook stuff. And then we're immediately going to translate it into something that just makes sense. Let's see if we can get that balance just right.
Okay, first up, the principle itself. At its absolute heart, this thing is a powerful rule for figuring out what happens when you have a bunch of different forces all acting at once. Think of it like the master key that unlocks much more complex problems down the road.
All right, deep breath, here it is. The professional textbook definition. It looks a little dense, I know, but the only two words you really need to focus on are vector sum. That's just a fancy way of saying we can't just add up the numbers. We also have to pay attention to the direction each force is pushing or pulling. This is exactly how you'd see it in a university lecture.
But, okay, let's strip away all that jargon for a second. The idea itself is actually incredibly simple. It just means that if you want to know the total force on something, you can ignore how all the forces might be interacting with each other. You just figure out each one all by itself, and then you add them up. That's it. It's that simple.
Okay, so adding up a few individual forces. That's pretty straightforward. But the real world is messy, right? It's rarely that neat. So what happens when a charge is all spread out? This is where the principle goes from being useful to being absolutely essential.
And this is the million-dollar question, isn't it? In reality, electric charge isn't always in one nice, tidy little spot. It can be smeared out along a wire, or spread across a metal plate, or even fill up an entire object. How in the world do you handle a situation like that?
Well, physicists have a really clever way of tackling this. They break it down into three main scenarios. First, you've got charge spread along a line. Then you have charge spread across a surface, and finally, you have charge spread through an entire 3D volume.
So let's just take these one at a time, starting with the simplest case. This is basically the one-dimensional version of the problem. You can think of it like all the charge is forced to stand in a single file line.
The perfect example here is just a long, thin wire. Imagine the electric charge is spread out evenly all the way along it. The charge isn't just at one point, it's everywhere along that line. That's a linear charge distribution, in a nutshell.
Okay, so that was 1D. Let's level up. Now we're going to expand into 2 dimensions. What happens when the charge has a whole area to spread out in?
For this one, I want you to picture something like a flat cookie sheet, or maybe a piece of aluminum foil. If you put an electric charge onto it, it doesn't just stay in one spot. It spreads out across that whole two-dimensional surface. And that's what we call a surface charge distribution.
And you know what's coming next. We've done 1D, we've done 2D. Now it's time to go full 3-dimensional.
So imagine a solid ball of plastic. The key here is that the charge isn't just sitting on the surface, on the outside. Nope. This time, it's mixed in throughout the entire thing, through its whole volume. And that's a volume charge distribution.
So, let's do a quick recap. Linear is 1D, for lines. Surface is 2D, for areas. And volume is 3D, for an entire space. So, 3 totally different ways that charge can be spread out. But, and this is the really cool part, they are all solved using the exact same core idea.
Okay, so this is the moment where it all clicks into place. We have this one simple principle on one hand and these 3 kind of complex-looking situations on the other. So how? How do they connect?
This is the big reveal. The secret, the aha moment, is that the one tool you use to solve all 3 of those messy problems is the superposition principle. It's actually genius. Physicists just pretend that the charged wire is made up of a billion tiny little point charges. Then they calculate the force from each tiny little piece, and then they just add them all up.
So what's so crucial to understand is that it all boils down to one single elegant idea. You don't need a new rule book for every different situation. You just need this one fundamental principle. Break a big problem into small pieces, and then just add up the results.
So why does any of this matter? Because it's basically a masterclass in problem solving. It lets us take a problem that looks completely impossible, like calculating the force from millions of charges at once, and turns it into something we can actually manage. And this whole break it down and add it up approach is a strategy that works way, way beyond physics.
And that leaves us with this final thought. This method, it isn't just for physics. Think about it. A huge project at work, a new skill you want to learn, any goal that just feels way too big. How can you chop it into smaller, more manageable pieces? The principle of superposition isn't just some random law of the universe. It's one of the most powerful strategies we have for turning complexity into clarity.